Hello friends, my name is Chinmay Deshpande, and in this video lecture we are going to discuss about the important topic of power system stability. The name of the topic is application of equal area criteria in that sudden change in mechanical input, or to be precise we can say sudden increase in the mechanical input. So let us consider that there is a one generator which is connected to infinite bus bar. Generator has an input mechanical power which is represented by Pm. Then E dash at an angle delta is the voltage of the generator with load angle delta. XD dash is nothing but reactance of the generator. X1 is the transmission line reactance with infinite bus bar voltage which is denoted as V equal to 1 per unit or 1 at an angle 0. Now how we can write the equation for electrical power PE? We can write it as E dash into V upon XD dash plus X1 sine delta. This term E dash into V upon XD dash plus X1, it will be treated as a Pmax, which is represented by equation number 1. Now based on this, here we have drawn a P delta curve. If you see here, this is delta which is on X axis, this is P on the Y axis, and this is your P delta curve. Now this PM0 is nothing but initial mechanical input. This 0 indicates that initial condition. Here you see point A. Now what you will see here at point A, PM0 will intersect to this curve. Basically this curve is nothing but what? This curve is of PE. So at initial condition we can write here, it is written under steady operating condition, or we can say at initial condition, PM0 equal to PE0 equal to Pmax into sine delta 0. Now we have to consider following points we need to taken into consideration. First one, there is no change in the torque angle, that is there is no change in the load angle delta when the speed of the rotor is exactly equal to synchronous speed. That is when omega equal to omega s, delta 0 will be equal to delta. This delta 0 indicates initial angle, or we can say initial operating condition. Now angle will be increased. Now when it will increase? When your mechanical input is greater than electrical output. As you know, acceleration will be equal to what? PA will be equal to PM minus PE. So if PM is greater than PE, then you will get answer as a positive, means it acts as a accelerating power. And the angle will be decreased when PM is less than PE. So that will treat as, again if you take this equation, then in that case what you will observe? You will observe PE is more than PM. So therefore PA will be equal to what? It will be equal to negative. Now let's discuss about the diagram which is drawn here. Before that, please understood this concept. PM0 is initial mechanical input, PE0 is the initial electrical output, PA is the accelerating power, and PM1, this one indicates sudden increase in a mechanical input. So I have redrawn this diagram here. One by one we will explain each point, what happens at point A, what happens at point B and point C. Now here if you see at point A, what you observe? Mechanical input is PM0. Please see it carefully. Here this is a point A. This is your mechanical input PM0. This will be your electrical output PE. So here we can say PM0 equal to PE0. So therefore acceleration will be equal to 0. Now as there is no any acceleration power, what is the speed? Speed will be equal to, exactly equal to synchronous speed, and load angle delta will be delta 0. So that's why here in the figure, here we have represented this as a delta 0 or a delta E0, whatever you can write as per your notation. Now what happens from point A to point B? Now here what you observe in the diagram from point A to point B. Here now mechanical input is suddenly increased from PM0 to PM1. So that's why this line indicates sudden increase in the mechanical input. So what happens in between A to B? Now as our mechanical input is suddenly increased, so therefore here I have written it is suddenly increased from PM0 to PM1. So what I can write? What will be your accelerating power? It will be positive. Now as acceleration or accelerating power is positive, or as it increases, rotor angle or the load angle delta starts increasing, and the rotor speed will also be increasing and the speed will be greater than synchronous speed, that is omega s. Now because of that, here the load angle delta will change from delta 0 to delta 1. So that's why if you observe from in between A to B, your delta will start increasing. Again, this is shown here in this diagram. Now whatever diagram which is shown here below, if you see, this will be your delta and this will be your time. So this is nothing but your swing curve. This is nothing but your swing curve, and whatever diagram here we have drawn, this diagram in between P and delta, this is called as power angle curve. So what you observe here in between A to B, if you see here in between A to B, this is your point A. Let's say I have taken this dotted line here. I have taken this, extended this dotted line here. So what you observe, this delta is going to increasing like this. So from delta 0 to, let's say, delta 1. Now what happens here after point or after region A to B? Let's say what happens at point B. Now here if you observe at point B, here it will be PM1 will be equal to PE. So this is your point B. So if PM1 equal to PE, what about accelerating power? Acceleration will be 0. But even though here accelerating power is 0, but due to a rotor inertia, the speed will not be equal to synchronous speed, or it will not drop down. That speed will be what? It will be greater than synchronous speed beyond B, and the rotor angle will increase from delta to delta 1. So how we can write the equation for accelerating power? PA will be equal to PM1 minus Pmax into sine delta 1. So let's see here at point B. At point B, the corresponding load angle is represented here as a delta 1. So here also you can see at point A it was delta 0 and it is now increasing up to this point. Again it will start increasing from delta 1 to delta 2, that we will discuss. Now what happens from point B to C, or you can write it as after point B, what happens? Now please see the diagram carefully. Here I am going to show it to you in the diagram. After point B to C, here this region, in between A to B, what was your omega? Omega was greater than omega s. Now after B to C, or in between B to C, what happens? Now omega will go on reducing, but still it is not equal to omega s due to the inertia of rotor. Now here what happens in between B to C? This curve, this is your one portion of the curve, this is your other portion of the curve. Here it is observed that PE will be greater than PM1. PE will be greater than PM1. So what happens because of that? If you put here PE is greater than PM1, then you will get accelerating power as a negative, which is treated as a deaccelerating power. Now your omega will start reducing, but still it is not equal to a synchronous speed. It will try to become, but it is not equal to synchronous speed. So that's why your rotor angle continues to increase up to some load angle, let's say delta 2, which is represented here, So up to delta 2, what happens? Up to delta 2, let's say it will swing or it will move. Now here, what happens at point C? At point C, omega equal to omega s. So what happens in that case? Here, the PM1 is exactly less than PE. So therefore, deaccelerating area and accelerating area both will be same. If you take this region, then what you observe? Here area A1 and area A2 will be exactly equal to the same. Area A1 is called as accelerating area. Area A2 is called as deaccelerating area. Now based on whatever diagram we have drawn, we will write equation for area A1 and area A2. Now please see it carefully here. I will open that diagram again. If you see this area A1, what is this? This is your upper limit and this will be curve, which is lower limit. So I am going to write it here. Area A1 will be equal to, what is the limit from delta 0 to delta 1, or delta is 0 to delta E1. So I will write it as delta 0 to delta 1. What is upper limit, which is represented by line? This line is nothing but sudden increase in mechanical input. So this will be PM1 minus this will be, what is this? This will be a curve. So it will be PE into d delta. So this is the mathematical equation for area A1. And why this area A1 is called as accelerating area? Because PM is greater than PE, and we already have discussed about this. PA equal to PM minus PE. So more the PM, more acceleration. That's why this region is called as accelerating area. Now how we will write an expression for area A2? I will write it here. Area A2 will be equal to what? Now upper limit is nothing but what? This is your upper limit, which is represented by PE, okay, and minus this is your lower limit, which will be PM1 into d delta. We forgot to write here limits. Limits will be what? It will be from delta 1 to delta 2. So please try to remember these equations. This is very easy but very important. Based on that, we have to solve few numericals also. So these are the equations associated with accelerating and deaccelerating area. Now here, if you see, what will be the maximum limit of that delta 2? Here initially it was, the point C was up to this only. But up to which limit, up to which value, which point your point C will go? So please see here, I have drawn this point C. Now here you will observe this line, first it intersect at point B. Please check where it will intersect to this curve at another side. So it will intersect to this curve at point C, means what? This will be your delta 2, or in other words you can say that this is nothing but your maximum value of load angle delta. Now we will discuss later on what is the significance of this maximum value of load delta. Now what you observe here, you know that already in a previous video we discussed about equal area criteria, and we discussed if area A2 is greater than or equal to area A1, then what is the case? System will be stable. If your area A1 is greater than area A2, then what is the case? System will be unstable. Now what you observe here, area A2 is greater than area A1, means system will be stable. Now what happens? What is the significance of this delta max? Let's say, suppose if your delta will start increasing after this point, if start increasing, what you will observe? Now after point C, your PE will reduce. What you observe? PE will reduce, but PM will be the constant, or which will be a maximum value. So if PE is reduced and PM1 is maximum, then if you put it here, PM1 minus PE, what you will observe? You will get answer as a positive, means again it will go into accelerating mode. And if it goes in the accelerating mode, then what happens? The system will be in a unstable manner. So the thing has been written here. What we have discussed here, any future increase in the PM1 means that the area available for A2 is less than A1. Please try to understand this sentence. Let's see, this is what is the PM1 here we have represented. Now suppose the PM1 is increased, let's say the mechanical input is increased up to this. If I write it as a PM2, what you will observe? This total area will act as a what? Not this, we can write it as this total area will act as a accelerating power, and this area will act as a deaccelerating power. Here what is observed? A2 will be less than A1, so the system will tend to become unstable. So this is what is the significance of maximum load angle delta. Now the system will remain stable even though the rotor angle oscillates beyond delta 2 equal to 90 degree, so long equal area criteria is met. The condition of delta 2 equal to 90 degree is meant for the use of steady state stability only and does not apply to transient case. After point C, which is shown in the figure 2, as deaccelerating power changes to accelerating power, system becomes unstable. Here see this point. After point C, now what happens? Again it will go into the accelerating mode, so therefore system will become unstable. So this is what is the topic that we have discussed in this video lecture. It is sudden change in the mechanical input. If you have any doubt, please feel free to ask. Thank you. Subscribe my channel, comment on this video and like the video. Thank you.